All right, we're back, still talking about special relativity. This lecture will have to do with relative velocity, classical relative velocity, and then the exactly correct relativistic method of calculating relative velocities. We have an observer. She sees two objects moving to her right at positive velocities relative to her. The velocity of object A with respect to O, the observer, the velocity of object B relative to O, the observer, is 6. Using the classical method of calculating relative velocities, we do the following. The velocity of A relative to B, that is to say what B says A is doing, is found this way. Applying this equation to these numbers, we have 10 minus 6, or 4. So B says A is traveling at 4 meters per second, positive. That means that she knows that with each passing second, A, moving faster than she is advancing 4 meters closer to her with each passing second. And vice versa. If you reverse the order of the subscripts here, we have the velocity of B according to A, which is the negative of that. So this number would say that the velocity of B with respect to A is a negative 4. That means that it's the same as if A is standing still and B is moving to its left at that velocity. Well, there is an exact equation that applies not only to the small velocities that we're looking at here, but even to velocities that are large fractions of the speed of light, c. The correct equation for the velocity of A with respect to B looks exactly like the classical equation in the numerator here, except there's this additional term downstairs. In the case where the velocities A and B are of the order of tens and 20s and hundreds of meters per second, the product of the two is still a number that is absurdly smaller than the square downstairs of the speed of light. And so for all practical mathematical purposes, that ratio at normal speeds is essentially 0. And 1 minus 0 is 1. And so this equation reduces to the classical equation. Well, now let's look at a case where the various velocities are not garden variety, normal velocities, 10s and 20s and 30s and hundreds of meters per second, but significant fractions of the speed of light. So look at this case. An observer sees object A moving at a velocity relative to her of negative 0.8 times c. Negative sign makes sense because this object is moving to the left relative to her. And she sees an object B moving to the right relative to her at 6/10 the speed of light. The classical result, this equation here, would tell us that the velocity of A with respect to B is negative 1.4 times the speed of light. But that's a big problem because nature does not allow relative velocities of anything to be greater or even equal to the speed of light. And so we have an exclamation mark there. This can't be. Fortunately, we have access to the correct equation for calculating relative velocities for all situations, small velocities and large ones. Well, the numerator, once again, same as that, negative 1.4. This turns out to be 0.8 times 0.6 is 0.48 with a negative sign. The c's cancel. And so the denominator becomes 1 minus a negative 0.48, or positive 1.48. Divided into the numerator, final result, 0.95 times the speed of light, safely within the bounds allowed by nature that no relative velocity can have a magnitude greater than the speed of light. That concludes our brief discussion of relative velocities. I hope you found it as exciting as I did.